Hello everyone, welcome back to Every Node in Godot Used and Explained. Today we will not be using or explaining any nodes in Godot. Uh, Okay, I have a good reason for it though. We are starting this series from the bottom. I did take a look at control nodes. That was a fun pilot episode, but I want to walk through every single node in Godot. And we will be starting with some very simple nodes like sprites and bodies. And I was going to do that right off the bat, but I realized as I was looking through the documentation that there's something even more fundamental. The variant, the most important data type in Godot. So before we can jump into the GPU particle extractor vector field 3D or the generic 6DOF joint 3D, we are going to look at variants. We are talking about the basic variant types. We are not going to be talking about object, which is a type of variant. We'll get to that one when we get to that one. But we're going to talk about all of these basic variants, what they are, what they do. I'm not going to assume that you know anything about programming. We're going to start from the very basics and work our way up as we go. Also, I will not be making a game within this video. My goal going forward is to make games out of these nodes. That's the used part of Used and Explained, but we are not using any nodes today, so I'm going to skip over that. Generally speaking, the goal for this is a lo-fi tutorial to relax and procrastinate to, as opposed to a very hyper-focused, let's just get it done quickly. So that is the goal overall. But yeah, let's jump in with variants. And before we talk about a variant itself, let's talk about a couple of the variant types. Now, I come from a C programming background, which is what we call a strongly typed language. So in something like C, if I wanted to create a integer, the first type we're going to look at, I would say int x equals 5. This is what we call strong typing. And it means we are declaring that this is a thing of type integer. I'll explain what that is in a minute, with a value of type integer. So we could never say x equals hello. That would be just silly because this is a thing of type integer and hello is not a integer. So in Godot, we don't write it like this. We say var x equals 5, and you'll notice it doesn't complain. And if I run this scene, there are no errors. This is the variant type working behind the scenes. So we'll get into the variant type, but I can do what's called strong typing. If I use a colon, it will say this is of type integer, and it will now say you can't redefine that. So that's what we're going to be doing up above. I am going to have our first type a integer, or int for short. And if you remember from math class, integers are any number, positive or negative, that is a whole number. So if I come in here and I type in 0.5, it rounds up to 1. What if I want something after that decimal point? Well, I can use a decimal type. Just kidding, it's a floating point. And the floating point has a decimal. Now you'll notice this only has 2 or 3 numbers in the editor. That's not actually how a floating point works. That is the limitation of the @export statement I have here. So if you didn't know, you can do a lot of exports. I'll refer you to the documentation if you want to see all of them. But if you want to have a little bit more freedom in your floats, so you can add a little bit more, and now we have much more freedom to work with. So this is a floating point type exported with a little bit more accuracy. So why is this called a floating point and not like a number with dot or decimal or something like that? Well, that gets into how computers work. And I'm going to explain this because we are going to be getting to way more advanced concepts and we will want this foundation going forward. If you want to skip ahead, feel free, but beware there are quaternions in this video, so if one eats you, it's not my fault. So here is a representation of an 8-bit number. We have these 8 individual boxes, and in a real computer, this is 0 or 1. Physically, this is actually more like a battery than a box where it can either be full or empty. We're going to simplify things and pretend that we have a decimal computer that can represent any value, so 0 to 9. The important thing is there are boxes. We can store any number from 0 to 100 million minus 1. And this is our range for an integer. Anything that we can fit in here, like 100, we can express. But we can't express anything that is larger than this. So if we go outside that range, we are actually going to lose some of that precision. So one or other end is going to fall off, and we are going to get a different number than we expected. This is a basic limitation of all computers. Don't worry, in reality, Godot uses 64 bits, which means you have a massive number to work with. So it's not just 0 to 10 million, but again, this is a simple example. So this is the way an integer would work, but a floating point is a little bit different. So we have these same 8 bits, except one of them is a decimal point. In reality, this is stored off to the side as a number representing where the decimal is, but we're just going to put the decimal in line because it's a little bit cleaner. So this is a floating point. And you may notice, we have one fewer decimal points of precision. So we can go up to 10 million minus 1 instead of 100 million minus 1. But you may also notice that this decimal point can move. So we can express the number 1 million in this. We can also express the number 1 millionth. Or is that 10 millionth? Whatever. We can express both of these numbers. We can also express 100.001, but we cannot express the number 1,000,000 and a half. This is too many bits, which means this will fall off. So we have a trade-off in a floating point between size and accuracy. So that's why it's called a floating point, because this decimal will float anywhere through the number, and it gives us a much larger range. It's also more complicated of a concept. It's harder to determine if a number will save properly. So the classic example is a third, 0.333 repeating. You only get a few bits of precision here before it falls off. So some of these numbers, if you start doing math with floating points, may not be perfect. Experienced computer programmers may be wondering, is that all I get, int and float? And yeah, for the most part. If you're doing something that needs more accuracy or more precision or more whatever, you may want to go to C# or C or GD extension. There are other options to do more accurate things, but for 99% of what we do in basic game development, you don't need more than this. So these are the two types we're given. So those are integers and floats. Of course, we have a lot more things here. We're going to introduce our next one real quick, which is the Boolean type. A Boolean is simply true or false. So there's actually a checkbox you'll see on or off. But if you want to assign this a value, you're going to assign it true or you're going to assign it false. That's a Boolean. I should actually assign values to the other one so you see how those work. So there we go, 0, 0.0. Again, I can also change this to a different number, and that works just fine too. Next up, we have a string. You may notice two interesting things with the string. One, this is capitalized. These ones were lower. And two, if I come over here to the string, I can type in as much stuff as I want. There doesn't seem to be any limit to it. So that's an interesting thing. We'll talk about why that is in a little bit. With these four types, we have enough to be able to stop and explain variants themselves. So I have another variable. And what do you think? Does var stand for variable or variant? The documentation seems to use both. Anyways, I'm going to set this to 0. This will be an integer. And I am going to do something fun. I have in here, I'm going to do if Boolean, and these you can use directly in an if statement. Other things you want to do a logic check, but I can just check this if it's true or if it's false. So if it's true, we're going to just say variant plus equals 1, and if it's false, we are going to say variant equals hello, which is a string. We are using this as an integer here, but we are using this as a string here. So if I double check, this is currently true. So I run this. Everything seems to work, nothing breaks. If I go to my remote view and I click on this node, you will see there are the members. This is what is active right now within this class instance. Down here, we have the base values. This is still set to 0. Up here, you'll see it's set to 1. So that seems to work. If I stop this, change it to false and run it again, now this remote variant is set to a string type. It says hello. And so this is changing its type under the hood dynamically. And everything we do is a variant, and this is a feature, not a bug, but there is a problem. If down here, I then want to say variant -1, this will work sometimes. If I set this back on and I run it, everything seems to work just fine. If I turn it off and run it, you get an error. You can't use a string and an int together in a subtraction. So this is a little bit of an issue, and it's why I really prefer strong typing. If I put the colon here, it will then highlight this and say, you can't do that, you can't reassign this. But if some people like weak typing, it does work. It just depends on what you want to do. But be aware of that either you'll get an error here saying you did something wrong, or you'll get a silent error that shows up when you're actually running the game when you try to do math using a string. So that is the variant. Let's introduce one more simple type. This is very much a video game centric thing, but we have a basic type of color. So if we come in here, I now have a color picker. See, it defaults to black, but I can set the opacity and then I can go grab any color I want. We'll do a, whatever this is, fuchsia, magenta, something, I don't know colors. We'll do that nice pastel purple color. And this is storing that color. We can use it and apply it everywhere. Next up, we have vectors, and there are actually a lot of these. So we'll just start with the vector2. All this really is a XY coordinate. If we have a XY plane here, like you might have had in algebra class way back when, you just have a dot and this is where the vector is. The thing though is we will often represent vectors with arrows instead of dots. So we have this arrow pointing to this dot out here. This is our vector. So you will often add vectors together to get a new vector. So you can have, a plus b equals c like this, and this third vector ends up being the end of these when you line them up head to tail. So this is how vectors work in two-dimensional space. As you imagine, we can have more dimensions, so we can add an extra axis back here, and this is the z-axis. Notice, because this is a two-dimensional screen, suddenly I have no context for where these are within that three-dimensional space. That is a little bit of an issue you have to deal with, and 4 dimensions is even harder to visualize. So this is the short and simple of how vectors work. You'll notice we have a bunch of vectors. There's the vector 2, but there's also a 2i, 3, 3i, 4, and 4i. I just means this vector uses an integer. So if I am swiping through, you'll see I only get whole numbers. And so this is useful for something like if you want to snap to every pixel on the screen, you can specify that XY coordinate using a vector 2i. So 3 and 4, we have X, Y, Z, and then X, Y, Z, W, because we ran out of alphabet. This is a little bit of a convention. We usually start with X, Y, Z. Vectors are something we'll continually come back to whenever we're doing positioning of 2D or 3D nodes within the scene view. Also, anything physics, it's any velocity or position. So we'll use it all the time, and oftentimes we'll be doing math with vectors. So this is something you do have to get a little bit used to, but again, it's not that complicated. It's just X and Y coordinate. So if you can imagine something in one dimension, just adding a number together, just add a second dimension on top of it, and that's a vector. This might just be my C++ background coming through, but I made mistakes early on using vectors. I would oftentimes have 3 or 4 values that I just wanted to store, and I would use a vector to do that. You don't actually want to. Vectors are specifically for values that are working together to define something in 2 or 3D space. So you see a lot of the functions in here, we have things like length. You can take the size of this vector. So if you have 2 values that aren't an X and Y coordinate, they're just 2 random numbers, what you want to use instead of a vector is a collection. So we have 2. The first one looks like this, and an array gives you the option to put any number of variants you want. So you'll see these default to null, and if I edit this, I can pick from a long list. So we'll make this one an integer, we'll make this one a string, and then we'll make this one a color. So we have all of these sitting together. Now, if you want to do something a little bit more specific, you actually have the option to do a even more strongly typed array than this. So if I want to do an int array, I can do an array of type int. And so this one will give us an array that only allows integers. So if I open this up, you'll see it didn't give me that option to pick a variant. Everything in here is an integer. And so you can do this for strongly typed arrays. But right now you can do an array of type array for a two-dimensional array, but you can't continue that and say of type int. This isn't supported, but you can do a array of type array if you want, and this does give you a two-dimensional array where each element gives you another array. So you could create arrays of type int and assign them into this array, but each one of these is its own thing, which is why you can't define them on multiple levels like that. But you can do an array of a special type, and it will default to only being filled with the values you want. So you can have this as a general collection or a specific one. There's a second collection that is quite useful. This one, let's say I want to look things up by name. Well, for that, I would use a dictionary. Now, this one is going to use curly brackets instead of angle brackets. And the way this works is it is key value pairs. So the array just has a bunch of numbers or colors or whatever you want to put in here. But this one gives you a key and a value. Now, you'll see I can pick probably string makes sense for this. Oh, I think click the other one, whatever. So this can be, I don't know, we'll say white, and then let's pick a color, and we will set this to white. So that is how you can put these in. Notice once I have this pair, I can't actually change the key. I can only change that value. So you can change what it references to, but I can't find an easy way to change what the key actually is other than just completely deleting it. So an easier way to work with dictionaries is to just put what you want in here, and then if you need to modify them, you can. Unfortunately, they don't have strong typing like the array, so you can't say string color. This doesn't work, which is a little bit unfortunate. It would be nice if we didn't have to specify the type each time for every individual one. But anyways, this is useful for looking things up by keys and values. We have one final type of collection to look at. And by one collection, I mean a whole bunch of them. They all serve the same purpose, though. These are additional arrays. So we had up here the array, and these ones are packed arrays. So it's an array of a certain type. If you want to actually use these, we'll come down here. I set up a couple things. So first off, if you want to add a number into an array, you can use the append function to put something at the end. Alternatively, if I want to assign a specific value, I can do an index. So array 0 equals, we'll say 44. And then when I say x equals array 0, it will get that number 44. If I move this up, it'll actually grab what was in there previously, which I think, oh, you know what, we assigned this here. So let's drop in a breakpoint and rerun the scene real quick. So we'll see here we have some local members for this every variant node. And if I come down here, we should see our array and our int array. So this is an array of size 3, and you'll see that 0 was a integer of number 55. As I step through and append, we'll see that this gets updated, and it makes me scroll every time, thank you for that, to an array of size 4. So this was put on the very end of that array. We'll see down here, number 4 is at the end. You can also add things to the front of the array, and you can reverse arrays, concatenate arrays, all sorts of functions you can do. Same thing with dictionaries. So if I do this, x equals array 4, we'll see that it pulled that 55 out. And then if we assign 44 and we go down to the array, we'll see once again, this has been assigned into that spot. Now the 0th position contains that number. Same thing with dictionaries. This dictionary is currently a size 3, and because black doesn't exist, when I set this one, it will become a dictionary of size 4. So these are very similar arrays and dictionaries. Again, if you come from a programming background, you may wonder, is that really all I get, arrays and dictionaries? And yeah, that is all you get. We don't have things like the linked list or binary trees or other things, but it isn't too hard to make those kind of data structures if you need them, or you can use another programming language to do a little bit more with data. But yeah, so here we go. This is now containing that blue. And then if I pull out red, we'll see that Y is now a color. So that is it for every container. Of course, we still have that question of why would you want to use a packed array? And for that, we really need to talk about performance. I have been a firmware programmer for about 8 years, so I'd like to think I'm a bit more of an expert on performance versus other areas. And this is something I tend to get wrong though with things like Godot, is I will optimize first, and that is usually the wrong choice. If you are just making a game, just make a game, just use the standard array, don't worry about it. If you are doing something where either the profiler tells you that you are having a performance issue, or you know in advance you're going to do something particularly complex, then maybe it's worth trying to think about performance. Generally speaking, I wouldn't say jump in and use a packed array right away if you don't know in advance that you'll need one. With that said, let's talk about a couple of situations where you might want to use one. So last year, I made Minecraft, and this was a game with a lot of data and a lot of objects. So for Minecraft, each chunk is, we'll say 16 blocks by 16 blocks by, I don't remember, I think it was 256 tall. That is 65,000 data objects. So if you take a look at the documentation, this is kind of crazy to me, but a variant is 20 bytes. And actually, it says it takes up only 20 bytes. That is kind of hilarious to me. 20 bytes is not an only in my mind, but apparently nowadays that is considered small. For reference, a 64-bit integer is 8 bytes. It's, 64 bits divided by 8 bits per byte is 8. So we have more than double that is the amount of bytes in a variant. So let's say I wanted to store something super simple. Let's say a Boolean that tracks if a block exists or doesn't exist within a chunk. Well, I am going to be taking this 65,000 objects and multiplying that by the 20 bytes. And this gets how many bytes we have in a single chunk. So we'll divide that by 1024 byte, kilobyte, megabyte. So that's over a megabyte of data just for that one chunk. And I had, I think, somewhere around 60,000 chunks in my best run. I was doing some testing there. You don't necessarily need to have that many, but still, that is a lot of data, adds up really quick. So being able to divide that by 20, for example, is a huge deal. So I actually use the PackedByteArray to track things like what type of chunk this is. So a PackedByteArray contains these 8-bit values, a single byte, and this is the smallest data type you can have. And the packed array takes them and arranges them all together side by side, as opposed to having variants that are containing those. And so this one in particular will actually save you 20 times the data compared to using just a integer or Boolean or whatever else you want. Of course, you can go even smaller if you're using a packed byte array. If you do some custom logic, you can store Booleans in there, 8 per byte. You can get a ton of flags crammed into here. And so I actually did break up this byte into each of these 6 faces in a block, saying, do I need to draw that face or not? Well, that data existed in a single byte, and I had 6 of those 8 bytes were used in one chunk for 6 flags. So if those were Booleans, we actually would have not been 20 times 6, so 120 times bigger if I had just used a bunch of Booleans. So these are useful to know, keep in your back pocket. And if you are either optimizing a game you already made or you're approaching something like a Minecraft clone and you know you're going to need it, that's where you want to go with the packed bytes. Interesting one down here is the PackedStringArray. This is interesting to me because strings are not the same size. Typically, the way an array will work is you can index into these and it'll just multiply by the index. So for indexing into a byte array, under the hood, it'll just multiply 1 byte by however many your index is, and that's the address. Where I don't know how that works for the PackedStringArray because each one is a different size. The documentation didn't seem to say much about how it packs the strings. It just says that it packs them tightly. So I'm assuming that these are inside that array. Now that may seem weird for me to say. Wouldn't these strings be inside the array all the time? That comes back to the question I asked earlier of why is this capitalized and these aren't? Well, in traditional programming context, you have 2 kinds of data. You have primitives and you have objects. Something like an int is actually just storing this number. Those boxes that we talked about are containing this number value. You remember I was typing a lot of stuff into the string, and it didn't matter how big it was, it still worked. So we'll have the string stored in a bunch of boxes somewhere else. And this can be as long as we want, but this first box is going to have a specific address. So we'll say that this is at address, I don't know, 101. And then this up here, instead of containing the entirety of the string, will simply contain that address. It'll say this is 101. So when you are accessing this variant type under the hood, it is using this is called a pointer. It'll use the pointer to find where the string is, and then it'll give you the string. So certain operations don't actually need to go and get the string. It can just check the pointer. You're saying, is object A the same as object B? Well, it just compares this number and says, yeah, it's pointing to the same thing. Of course, if you want to check something like a string to say, do these strings say the same thing? You need to go get these strings and compare those strings. There's an opportunity for optimization here then. If we have multiple strings, they will each get assigned their own address. So we'll say that. And if you create 4 of them, each one will be pointing to its own physical space where the string is stored. So when you imagine if you have a system in a game where a bunch of objects have references to, let's say, the character that owns the object, and you decide to use a string for this, you will have the same character's name hundreds or thousands of times throughout your project. And each time it'll be taking up a little bit of memory, and more crucially, it will be compared, doing this deep comparison of all of these individual letters within the string to see, are these essentially the same? It's possible that there's some level of hashing that may happen there in the comparison. I don't know, but it still does take time. So what if we could have every one of these references point to the exact same string object if it is the same letters within the string? Well, that exists. It is called a string name. And for this one, you just put an ampersand in front of the string. So this is exactly the same thing as a string, except this acts more like a singleton, where if I have a second string name, we'll just say string name 2, and this one is pointing to the word hello, it is now referencing the same physical space where this one is. Obviously, you can change this and this will work just fine. You know, it's safe to use, but this is a kind of string singleton type. So I set up a string comparison demo over here. We're going to compare 2 strings. We'll do it 10,000 times just to see how long it takes. So the first one is a standard string and the second one is a string name. And you see here, all 4 strings say hello. So these are identical in contents, but again, string 1 and string 2 are 2 physically different string objects. String name 1 and 2, they're 2 different variants, but they're pointing to the same address space. And we'll see that this one took 4 seconds and this one took 3 seconds. That's not a super interesting demo, so I decided to grab a slightly larger string. I heard that War and Peace is a nice small book, so I grabbed the entirety of that in plain text and put that into all 4 of these strings. If I rerun this now, it will take quite a bit longer. Previously, we were, 3 and 4 milliseconds? Now we have 3 seconds versus 6 milliseconds. So it did take a little bit longer to compare these, which is interesting, but you'll see this is a massive multiple orders of magnitude slower when you're comparing strings versus string names. So if you're doing something like using this as a key in a dictionary, it might be worth using a string name. The documentation was talking about how string names are often used inside the engine in various places. So I don't know what will be optimized by using this versus what automatically is converted to a string name, but either way, I think it's worth doing this if you are using a bunch of the same strings in places and need to compare them to themselves oftentimes, like accessing a dictionary, for example. This mentioned, see also NodePath. This is the final string type. Coming back to this, we have a NodePath is just a string with a caret in front instead of the ampersand. And of course, nothing in front is a standard string. The cool thing though, I added a couple random nodes in here, and with a node path, this is specifically a string designed to point to a node. So I can click here and I get a selector. This is something I desperately wish I knew about earlier. Generally speaking, you want to call down, signal up. So the proper way to use the Godot engine is to grab this, drag it in, hold control, and you get a reference to the button. And that's great because the button is a child of this node, so everything works just fine. But if I want to access a parent node or a sibling node, a child of a parent, I could do something like this, which is a horrible, horrible idea because I don't know that the node is going to stay here. It's going to keep the name. Doing this breaks things. So you don't want to be referencing nodes that are above you or beside you, especially if you're working between scenes. If I save something here as a sub scene, say branches scene, I can't access these sibling nodes, but every now and then it is useful. Say I have a player and I want to be able to directly update the GUI elements. Maybe isn't the best example, but I've done a lot of game scripts in the past where I'm basically sending out a signal that is being handled by the game script and then calling into, these little checkboxes and buttons and health bars that I don't want to have to add scripts to. They're simple objects. Well, here I can just have a direct reference, and when I put one of these inside my scene tree, I can come in and I can select the node path specifically. Note that this is still a path, it's a string type. So if I want to do node path, and this is a button that I'm getting. So if I wanted to say disabled, this is going to say, nope, that doesn't work. That property doesn't exist. So I still need to use get node on that node path string, and then this gives me the node. But as it mentioned in the documentation, this is pre-parsed, meaning I don't really have to worry about this being an invalid path because I've selected it through the editor. There is a pretty clear link here that yes, this is the node I want. I clicked on it and selected it. There's no risk of typos. So that is a useful string option. Now this get node function, you might expect this to return a node type, which isn't wrong, but if you were to take the type of this function, you'll actually see that it returns an object. And that's because we only have a total of 38 types. So if I come to the variant types, we'll see that we have all of these that we talked about today, and then we have the object. And everything is an object. This is base class for all other classes in the engine. So everything that isn't a base variant is an object. So we will spend a lot more time with these. A couple things object related we should mention. One type, the resource ID. This one is a little bit more complicated. It will tell you that it is used in the low-level server classes. You don't need to use the scene tree at all when making games. If you are doing a whole bunch of creating, let's say, meshes, you can pass them into a rendering server, and in order to manage these meshes, you don't need to have references to them directly. You can instead convert them to a resource ID, which is kind of like a specialized pointer or a dictionary key. I guess dictionary key is a better way to think of it because you can't just dereference this to get your value, but it is a key to find your object in this server. So if you want to manage things, you can just use these resource IDs instead of passing around the actual meshes. And yeah, you don't need to use the scene tree at all. This is something I'll definitely be revisiting when we start talking about some of these more advanced options, but this is another base variant type. On the topic of nodes, another important thing we can do is deal with the functions here that are attached to nodes through these scripts. So obviously you can just call a function directly if you want. This is something that we do all the time, but there are a couple cool ways to connect functions to each other. So the first one is going to be the signal, which is a variant type. So this actually is created with the signal word. And so I will have did thing. When I create this, it will be automatically added over here to the signals under this node. And if I double click on it, it will give me the option to connect to a function. So we'll say receiver method is a function called didThing, and it will have a little indicator that this is now connected. So if I call emit signal didThing, it will send a signal that will then be received and will then call this function. I don't have to connect it this way though. So if I could do another signal, I can connect it through code. After I emit this one signal, I can then say connect did other thing to, and you'll notice this asks for a callable. So I will call the function, except I'm going to get rid of these parentheses around it. So if I have the parentheses, it will call the function and it will return its value. If I don't have these parentheses, it will actually pass the function itself as a callable. So I can then do the same thing. I can say emit signal did other thing. Let's run this and see what it does. So here we are emitting this first signal, and because I connected this through that inspector over there, it will come through and call this function, did a thing. And so we'll see on the output that it printed that message. And then I'm going to connect this signal to this other function. So this is happening in real time in the script. And when I emit this signal, sure enough, it will call this function, did other thing. And again, we'll see that it printed did another thing. In Godot 3, that was all we could really do. You had signals for connecting things. But in Godot 4, I can do something a little bit more, we'll say, object-oriented. I can create a callable variable here, and I can set it to my third function, did a third thing. So instead of connecting a signal here, I can simply say callable equals did a third thing. And again, you get rid of this call because I want a reference to the function itself as opposed to calling the function and getting the value it gave you. And now I can do callable.call. And when I do that, it will call this third one. So we will run this one more time. We'll see that we emitted a signal, we did a thing, we'll connect the second one, emit that second signal, did another thing, and finally we'll assign this callable. I'm going to scroll down in these stack variables and we'll see it just says it's a callable. It doesn't give me much information, but I did set it. So if I press enter, sure enough, we called into this function and there we go. We have all three of these things have been printed. So if you want to pass around objects and functions, you can use signals, which is the traditional Godot architecture, or you can use this first order approach of passing around functions as objects and using the callables for that. So these are the signal and callable variants. An important distinction here with the signals is you can have a signal connected to as many functions as you want. So even though this one is already connected, I can go and I can connect a second time to a second function, and we now have two functions that get called from that one signal. So we can do as many connections as we want, which is useful, versus passing around callables directly, you are handling just that one function. So signals are more versatile, but these are two options for dealing with functions indirectly. We are down to our last few variants. So we have a final category of transformations and rotations. We'll start with the most simple of these and work our way down. The rectangle is just a rectangle. It has two vector 2s representing a position and a size. So I made a quick demo here to show this off. All right, so we have a rectangle sitting here in the scene, and you'll notice we have a origin and we have a width and height. These are two vectors. So if I turn on the grid here and I move this origin around, you'll see that this size comes with it. And if I turn on the updates, you'll see that this rectangle is following. Now, if I want to change the size of the rectangle, I just move the X or the Y, and it will adjust the size of that rectangle in those directions. Notice here that X is positive, but Y is actually reversed, where down is positive. The top left of the screen represents 0, 0. So in that sense, the vertical axis is reversed from a standard mathematics class. That's all that this does. We have this position here that gets put into the origin, and this one here is put into the size. I'm visualizing this using an actual rectangle, so I can come in here and I can change something like the rotation, but we don't have that for this basic rectangle variant. It is just these four numbers that define it. These are used all the time for collision detection mainly, and so if you want to calculate does something overlap with something else, using a rectangle is super fast and easy to do. Again, there is an integer variant, so if I come into these ones, we'll see that our rectangle, this one is a float, and this one is an int. Next up, we have the Transform2D, which is one step above a rectangle. Now, if I come into an object that has a transform, we'll see there's a size, a position, a rotation, a scale, and a pivot offset. That is not how a transform works. These are useful ways that you can modify a transform. So if I come into this 2D scene, you'll see I have a color rectangle. It's got a 0 size. There it is. And I can move this around and I can snap it to different sizes and positions and scales and a pivot offset. What even is this? Yeah, there's a lot of various things that you can do here, but under the hood, a transform, just like a rectangle, is a couple of vectors. This one has 3 instead of 2. So before we had a position, x, y, and a size, width, and height. Now we have a position, x and y of the origin, and then a position for the x and a position for the y. Coming back to this little demo, I turn off updates for a second, we'll see that we have the Transform2D origin, we have the Transform2D X, and we have the Transform2D Y. So if I move the Y up here, and then we turn on the updates, we'll see that this flips upside down. And actually, I can move this around. Now, notice when I'm doing this, we are actually scaling this. So it is determining the size of this object based on these three numbers. Now, I have divided this by the size of the sprite, but in reality, this is currently a scale of 1. So the x is in the position 1, 0, the y is in the position 0, 1, and this is the default. But if I wanted to rotate this, I could take the X and I could move it up here. I could take the Y and I could move it over here. And because these are still 90 degrees to each other, when I start this, you will see that this object has been rotated. If you're counting, you may have realized we only covered 5 axes of movement. We have the position in the X and Y space, we have the width on the X, we have the width on the Y, and then finally we have the rotation value. So there's still one axis of movement unaccounted for. Final axis is actually shear. Right now I have this X and Y locked to be perpendicular, but I don't necessarily need to do that. I can drag this off to the side and this sprite will shear. And so all of these are affecting this transform here. You'll see this skew value is showing up here. So we have our 1, 2, 3, 4, 5, 6. But again, this is a representation, an abstraction of what we're doing. So I have a tool script here, but this is setting these based off these little marker objects. So we'll see that I am setting the position of a rectangle based on the origin and the size based off the height. This is actually using a transform. I just wanted to demonstrate what a rectangle would do. But for this one, we are actually building a transform 2D, and we take the X position, we take the Y position, and then we take the origin. And I'm dividing by 64 because that is the size of the sprite, just to make sure that these handles appear on the outside of this object. So yeah, those are the 2D rectangles and transforms, but we can add a dimension to it. Now, I'm not going to build the same demo, so I ended up making the same demo in 3D space. To start, we had the rectangle, which if you remember was just an origin and a width and height. Well, we have the exact same thing in 3-dimensional space. So this is the axis aligned bounding box. This is a 3-dimensional box, but it is determined by a origin over here and a width, height, and depth over here. So if I come back into the every variant, we'll see that the AABB, it's funny that this gets shortened, but a visual shader node texture parameter triplanar is just fine without an acronym. I'm sure that there's a math reason for this being shortened, but I just found that kind of funny. But yeah, so the axis line bounding box, or AABB, is just a X, Y, a Z, a width, height, and a depth. And you can see this is what this would look like in 3D. So this would be a box of 1, 1, 1, 1. And as we move the origin, the object moves with. And if I actually set this one up properly, it would scale as the green one moved. So that is the AABB. So in 2D, our next step was the transform, but in 3D, there's going to be an intermediate step. We have the basis, which is a way of representing scaling and rotation. So I have here this little tool, which looks very similar if you look up in the corner. We have the X, Y, and Z. And if I put a object in the middle of this, as I move these around, we'll see that the object scales with them. And just like in 2 dimensions, not only can I adjust the size in any of these 3 directions or the rotation by spinning this whole object, I can also affect the shear of this object. So you can change the shape and the deformation and the rotation. So all 3 of these can be done by moving these 3 points. So this is the basis. It is represented, it's 9 numbers, but it's really just these 3 vectors representing where the X is, where the Y is, and where the Z is. So the basis is always sitting just at the location 0, 0. This is just representing how it is rotated and scaled. So if you ever call transform.basis, this is what you're getting, is the I don't care where I am, just what am I facing or how am I sized. That information is stored here. The transform 3D is a basis, these 3 vectors plus the origin vector. So coming back in, we'll see that we have not only these 3 balls, but also the black one in the center. This is the origin. So as I am moving this origin around, the object will move with it. So you can move the where the object is, and then you can adjust each of these individually to how is the object rotated or deformed. Of course, rotating and scaling are way more common than deforming, but unfortunately I made this demo a little hard to rotate things easily, so it gets deformed as I move it. But you can see the idea as we're moving around these four vectors, we are getting a distortion of the object to match. At its most basic, the Transform3D are these four vectors. We don't actually have a Euler angle type. That's just a part of the Transform3D. If it shows you your rotations, notice that you can actually set this to basis and you can rotate by modifying these three vectors exactly as I was doing in this demo by dragging things around and modify each of these three vectors. Of course, Euler angles is the default, but Euler angles aren't actually a type. They're just an expression, a convenient way of seeing how these work. These 12 numbers is everything that a Transform3D is, and everything else is derived. With that said, there are some issues that you can run into. So I have a different demo here for rotations, and I did an entire video on this. I ended up breaking it out, but basically there's an issue with trying to use these kinds of rotation. This is Euler mode, and if I rotate the Y, you'll notice this is spinning in this direction. If I rotate the Z, it spins in the same direction. If you don't know why that is, I will point you to my demo, but a quick version of this is that we have Euler angles versus Quaternions, and these are two ways to express rotations. So we were using the basis and the transform for just setting a rotation that actually works pretty well. If you can say, hey, I know which direction is my forward, and I know which direction is my left, and I know which direction is my up, well, using those three, you have a basis. So you can easily set where it is and what direction it's facing in world space using that. But if you want to rotate things once they've already been put in world space, in Euler angles, you get 1, 2, and 3. And this is actually, this gimbal is a accurate representation of how this works. So if I rotate it 90, we'll see this issue I had earlier where spinning this one and spinning this one do the same thing. And so here we have Quaternions, which is basically a vector that you can set. This is a three-dimensional vector. You set a rotation in degrees, and when I click rotate, it spins around that vector. So if I go the other way, it will rotate this direction around that vector. So this is the X, Y, and Z, and then the W. These together form the vector direction and a rotation around it. Going back to that Quaternion demo, you can actually see as I am choosing various X, Y, and Z components, and then I am setting a rotation around it, that these are the X, Y, Z, and W values. So again, I did a dedicated video on that. I won't go into extra details here, but this is how you were to rotate an object about this vector. Finally, we have a plane in Hessian normal form. I'm going to pretend to know what that is. Again, there are constructors here to make this easier, so I would probably use the one where you pick a normal and you pick a point in 3D space where this is. But this will generate a plane. And so the way the normal works is you have this plane here is sitting at a 90-degree angle to this normal vector. It's 90 degrees in all directions. And so as this plane rotates and moves, that normal vector also moves. Finally, the last one is a projection, which I saved for last because this is a thing that is used pretty much exclusively for cameras. So a projection is a 4x4 matrix used for 3D projective transformations. I did see an interesting video on this a while back, so I will link that. But this is something we'll talk about more when we use the camera 3D, because I've never had to create a projection matrix before. But this does give you the ability to do more advanced things with the camera if you want to mess around with it. But yeah, this is also a variant. So that was it. Tried to be a short video. I guess it wasn't. But anyways, this was every variant. So we have the basics of integers and booleans and strings. We worked our way up through vectors, and then the collections, arrays, and dictionaries, and all of the packed arrays. We had some of the callables and the signals, and then the basic object itself. And finally, we have all of these transformations and rotations. So you can define rectangles and axis line bounding boxes, and then finally the basis and transforms themselves, and then some of these helper functions like a Quaternion. So that was it. I'll probably be coming back with something a little simpler, like just the basic, bodies and sprites. But I wanted to cover every variant before we moved on. Let me know what you think. I did notice that somebody else also made a Every Node series, but there seemed to be a little bit faster. And so I think I'm going to keep going at just a slower pace and really try to dive into how everything works. And then also, take time, have fun with it. I'm going to be making a bunch of games as a part of this. And so I'll be showing off how these nodes can be used in a more theoretical context. So yeah, that's it. I will see you in the next one. And thank you so much for watching.